All right, now we're going to start talking about some more advanced topics here in section 4. With video 8, we're going to be working with subroutines in ladder logic. We're going to talk about the benefits of modular programming and how to go about creating and calling subroutines. I want to take my time with this instruction. This is the masked equal. This might be a little confusing to think about. If you are familiar with decimal, binary, hexadecimal, that would be very helpful. And I would suggest reviewing it. I think I actually have a video somewhere in the channel from a few months ago where I actually go through number systems. But if you are very familiar with it, this might not be that difficult. Probably the first step I want to do is maybe bring up the actual help on the instruction, which is really good that you have this available. This is a conditional instruction. It's a comparison, but it's a masked equal, and you're actually comparing 16 bits with another set of 16 bits. So you know the binary files, the B3 binary files, like in this example here in the help, B316, it's a 16-bit um, register. So you're comparing a source um, with the compare register, and there's a mask. So I'll just kind of read through this. It says a conditional instruction compares 16-bit data of a source address to 16-bit data of a reference address through a mask. If the values match, the instruction is true. This instruction allows portions of the data to be masked by a separate word. And I'll get into what that actually means. The source would be the address of the value you want to compare. The mask is the address of a mask through which the instruction moves data. The mask can also be a hexadecimal value. So if you're familiar with hexadecimal, basically it goes from 0 to F. There's 16 possible digits in hexadecimal. And that might be confusing, which is where you might want to take a step back and review number systems if you're not familiar with that um, before you come back to this video. But you can enter the value for the mask in either binary, decimal, or hexadecimal, whichever is easiest for you. RSLogix Micro will make any necessary conversion, and it'll display that mask in a hexadecimal value. So in other words, if you had F hex is equal to all 16 bits being turned on. Okay, so you basically have in hexadecimal 0 through 9, and then you have A is equivalent to 10 decimal, B is equivalent to 11 decimal, all the way up to F, which is equivalent to um, 16 decimal. I'm sorry, I didn't mean to mean all 16 bits are on. I'm sorry, I'm actually wrong about that. That is, F hex is equal to 16 in decimal, not 16 bits being on. So I'm incorrect about that. But you can click this link. There's a link in here to actually show you about how to enter the value. Um, you can use this method when you're entering the mask parameter. Um, you enter you can enter a hexadecimal mask. You could type the value followed by the letter H for hexadecimal. You can enter it in as binary and put a B after the N. And again, binary, your possibilities are either 0 or 1. Or you can type a decimal mask, whatever is easiest for you. However, you want to enter that when you enter the instruction. I just went ahead and entered it in hex myself. But this is an important part. The mask acts like a filter. You might not want to compare all 16 bits of your source address with the address you want to compare. You might only want to look at the first 4 bits, or maybe you only want to compare the last 8 bits. So the mask acts like a filter. The pattern of characters in the mask determines which bits will be passed from the source to the destination and which bits will be masked. Only bits in the mask that are set to 1 will pass data to the destination. All right, so they give you an example here and a move instruction. So they give you an example of a masked move. We're not going to get into the masked move yet. We're looking at this masked the equal here. So it might be helpful to look at the data table. I have a mask of F hex. So now I can go look at the data table. I can right click here, go to the data table, and you can see there's F hex in here for B306, right? Or B36. And the radix is how you want to display the values. I can look at this in binary, which is probably going to be a little confusing because I'm going to be looking at all the individual bits. But you can see that F hex is equal to, you have all zeros here. Bit 15 is 0, all the way up, through bit 4 is 0, and then bit 3 is a 1, bit 2 is a 1, bit 1 is a 1. So the first lower order bits are all ones here. So my mask is only going to be looking at the four lowest bits, bit 0 through bit 3 of that word. And you can look at that in decimal too. And I'm sorry, F here is 15. So yeah, 15 is the decimal value here. I think I might have said 16 earlier when I wasn't thinking, but the mask here is these 4 bits. So we're only really concerned with these 4 bits. So if you look at the example that I've got, you'll notice that B303 is on. So that means this masked equal is true. Now look at the source value that we have here. We have this number in B35, and when you look at this, the right number bits, this is bit 0 all the way to the right. Bit 0 is a 1, bit 1 is a 1, bit 2 is a 1. Bit number 15 is all the way to the left, and that's a 0. So really, these first 4 bits is all I'm looking at because of the mask. The mask is having me look at just 0, 1, 1, 1 on the right side, and I'm comparing that with 0, 1, 1, 1 on the compare. Well, 0, 1, 1, 1 is equivalent to 0, 1, 1, 1 in B37, so yeah, this is true. It doesn't matter that the other bits in both words do not match because I'm only looking at the lower order bits. Now, if I would go in here and change one of these first 4, let's say I make bit 1 a 0, all of a sudden this no longer matches because I changed one of the bits that's being passed through the mask. So again, this is a little more complex instruction. You have to think about it, but it's kind of nice because if you've got a whole bunch of inputs or a bunch of Booleans that you want to compare, but you don't want to necessarily compare the entire 16-bit register, there's only certain ones you want to compare. Using a mask will allow you to mask out the stuff that you're not concerned about. So I hope this has been helpful. I can see where this one might be a little more confusing and you might want to spend some more time looking at it. It's maybe not as often used as some of the other instructions, but it is a very useful one. All right, so I want to start out a little bit talking about some control instructions. We're going to get into subroutines, but there's actually a larger group of control instructions which really change the order in which the processor scans a ladder program. Typically, these instructions would be used to minimize your scan time in the PLC and create a much more efficient program, and it also can aid in troubleshooting. And not all of these instructions are available with all processors, so you need to refer to specific instructions. With the MicroLogix 1000, for example, that's a very low-end PLC, so not all the instructions may be available with the MicroLogix 1000. But you have a wide range of instructions in here going from the jump statement, the JMP, which allows you to jump forward or backward to a label instruction. You can jump to a label, which is the LBL. You've got a jump to a designated subroutine, which is I typically JSRs are something that I use quite a bit, jump to subroutine. It really helps create modular programming. I know when I first started programming, I used to think you put everything in the same ladder file, like ladder 2. But that's actually kind of poor programming. You want to break up different functions and put them in different routines. It makes for a lot cleaner code. And we're going to go into that a little bit further. There's also another instruction, the MCR, which enables or inhibits a master control zone in your ladder program. Also TND, which I've only used that maybe once in 30 years, but you can truncate a program scan, which is kind of an interesting instruction. I've only really seen that used in one application. Then you've got a debug or diagnose your user program. I'll be honest, I have not used that one. Program an interrupt label. You can interrupt. And so there's a number of different instructions. I would say some of the most common ones for me would be the jump, the label, the JSR, jump to subroutine, the actual subroutine instruction, and the return. The JSR kind of looks like this, where you have jump to subroutine, and then you list the file number. And remember, in the interface here, you've got these 16 ladder programs here available for you. You can go in the properties here if you wish, and you can say you've got a total of 17 ladder files created here, and you can name these, you can comment them. The standard is that ladder 2 is considered your main program. So I like to use ladder 2 as the main program, where I may have a lot of jump to subroutine instructions. And then I will typically use these other ones here, these blank ones, and create and have different instructions. Like maybe I have um, a program dealing in selecting automatic or manual modes. You know, you may have another routine that just has some output instructions, things like that. You want to break out programs logically and use some of these ladder routines. But we're going to discuss that a little bit more in detail. We're actually going to get into some, real world type examples, and we're going to get into more of the coding. But first, I want to give a good background of the various instructions available. All right, I wanted to go through a brief example here using the jump to subroutine JSR instruction and using some modular programming concepts. Now, first of all, I'm going to say this is not necessarily a great example of how to do modular programming. I'm going to just do a quick example where I'm showing how to do this with two different motor controls. Um, I would say a lot of cases you might want those motor controls in the same routine, possibly. This is not necessarily, we're going to get into some more real world examples and we're going to break things out logically. But the point of this is just to show you how the JSR instructions work, how calling subroutines work. So again, the JSR instruction is a jump to subroutine, and ladder 2 is by default, this would be considered your main program. This is the one that's going to always be running. And this is where I would normally put my jump to subroutines. Like if I'm going to have different routines, this would be where I'm going to call them from. In this example, I've got one that I'm calling motor 1, which is actually file number 6. And if you look over here on the left, ladder 6, I've named it motor 1. And then my second jump to subroutine is calling file number 7. And over here on the left, you see I've named ladder 7 motor 2. I can actually not double click. I want to right click on that, I'm sorry, and look at the program file properties, and you give it a name. Now, you cannot put spaces in here, but you can see for file number 6, I've called it motor 1, and I have a description, just simple motor 1. And then ladder 7, I've changed that. I've named it motor 2 as the file name, and then the description is just motor 2. Just really simple, just for an example. Apparently, I accidentally must have turned on a force here. I did not mean to do that. Let me try to fix that here. I did not mean to have forces on in the program. It doesn't really matter though, honestly, for the example that we're doing. I'll get into forces too. You can actually force I/O in this case, and I must have accidentally clicked that. But for our example here, we have ladder number 6, which is motor 1. Now, it's being called from our main program. Now, I can have conditions on these too. I could have some kind of conditional input that has to be made before I call this routine. And this is also good programming for scan times. You know, if you have routines that you don't want to have running all the time, you could put conditions in front of them and only call them when you need them, and that would be a good use for this. But again, motor 1 is just the normal start-stop circuit that we've used before. I've got and I don't need to go through and turn these on and off, but you've got your start button, your stop button for motor 1, and then the output for motor 1. And then really the second program here, ladder 7, is the same kind of thing, except this is for motor 2. Um, and you've got all these different programs here. You've got, ladders 6, 7, 8, 9, for a this is a MicroLogix 1000 that I'm simulating. I could have routines for other things in here too, which is quite helpful. But just wanted to give a little overview here of the JSR and how those work. And I really should probably talk about the SBR instruction. There's a subroutine instruction that's valid for all MicroLogix processors. Um, Again, you want to use a subroutine to store any kind of recurring sections of program logic that you might have to execute from different points in the program. In our case, we've just got ladder 2 calling a motor 1 and a motor 2 program, right? So not that critical. But um, it's this is an actual optional instruction. Normally, this would be put at the first instruction in a subroutine file, and it kind of helps identify the instruction. It's really kind of more or less an identifier. In this case, it really has no control bits. It's always evaluated as being true. And it would, again, it has to be as programmed as the first instruction of the first rung of a subroutine. And it's optional but recommended. Now, I didn't do that here. A lot of times in these simple programs, I don't bother to put it in here. I could have had an SBR instruction just to help identify it, but in this case, I did not. And again, here's our example here with the motor 1 subroutine. I could put this instruction up here. There's really no parameters involved in this one. Um, of course, there is an output missing on the rung. You are required to put an output on this, so let me just go ahead and put a dummy bit in here. I'm just make something up. E35, for example. Um, I don't know. Subroutine 6, SBR 6, okay. Whatever I want to put there for that. And let's see. Oh, I forgot to put it to the bit level. That's my bad. SBR 6. Now we should be okay now. It's part of the things you go through. But yeah, so there I put it in there. It's really not needed. It's an optional instruction. I mean, visually, when I look at this code, I go, oh, this must be a subroutine because it has an SBR. But there's no parameters that you pass in this or anything like that. So I know there are some other instructions where you can actually pass parameters from a main program into a subroutine and back out, but this would not be for that. Now, what I can do here is I can go system comms. There's my MicroLogix 1000 that I'm emulating. Remember, we're doing the emulator. I can do a download and go online. And first thing I need to do is put it back in run mode. So I'm going to do that. And there it is. So it's really, again, that's an optional instruction, but you could put it in there if you wanted to. All right, that is the SBR. Okay, I want to cover the jump instruction, the jump on the label really quick. And this is not really a real world example, but it's just a made up one just to try to show the use of it. I've got a rung here, rung number 2, This isn't our motor program, but that's kind of irrelevant here for this example. But I have a jump instruction, and the Q6 means that, yeah, we're in ladder 6, and then the colon, and then the 50. The label is 50. I could have made that anything I wanted. It could be 1, 2, 5, any number. I just chose 50. So this jump instruction is going to be associated with this label, and the labels must be the same. So if I'm going to jump to label 50, this is label 50. So I use the same thing here. Now, I also have a return statement. A return statement means that when this subroutine executes and it sees the return, this is normally going to be the last rung that it looks at. We're not going to execute rung number 3 under most, I'm sorry, rung number 5 here, where the label is. We're not going to execute that under most conditions. And you see that B307 is off over here to the right. If I go back up here, right now the jump is not being executed because B305 is not on. So I can toggle the bit. Look what happens. I toggle the bit, the jump instruction's activated, it jumps to label 50, which is here in rung number 5, and now my output bit B307 is turned on. Now notice what happens though when I go back up to rung number 2 and I toggle this bit back off. I toggled B305 off. You'll notice that B307 is still on, and you might be thinking, well, why would it be on? Because now I'm no longer jumping to label 50. I'm only executing up to rung number 4 where the return is, and I'm ignoring rung number 5. So why would B307 be on? Well, one thing to keep in mind, and this has gotten me a few times in programs, is that we're no longer executing rung number 5, right? But the last time we did execute rung number 5, B307 was turned on. So even though it's not executing, it holds the last state that we gave it, which was a 1. If I can go up here and I can actually toggle this back off, and I'm allowed to do that because this rung's no longer executing. If it was executing, I wouldn't be able just to simply toggle it off because the rung would turn it right back on. So that's one of the gotchas. You need to watch that, especially when you get into subroutines. You need to double check and make sure you're actually executing it. You know, I've seen things like where if you're not executing a rung and you have a timer, and it looks like everything in front of the timer should be making that timer increment. The timer's not incrementing because the rung itself is not being executed. So I just wanted to cover that really quick as well.